So let's together walk through one example. Okay, now this is the partition matrix expression. I've gone ahead and just made it so that it expresses what y top needs to be and what y bottom needs to be, and then this line delineates the two. What's on the right we'll get to in a little bit. And notice that to come up with loop invariance, what do? We say, well, some of the computation has not yet been done. So let's take away this and this. Okay? Actually, there's a problem with this one. Why? Well, you want to find a loop guard so that you're done, right? Notice that if a top left is all of a, then x top is all of x, so this becomes a times x, and because sizes have to match, y top is all of y, so you get y is equal to a times x plus y hat, and you've computed the final result. And notice that y bottom would have no elements in it, and this would disappear for similar reasons, and everything is good. So the point is, you can come up with a loop guard such that when the loop guard becomes false, you've computed the correct result. So far so good. But then let's go to the top and say, is there an initialization step that will put us in this state, given that when we start, we're in the state where y is equal to y hat? And there we have a problem, because if you say, well, let's take a top left to be 0 by 0, we're going to be marching from top left to bottom right, then inherently a bottom right is all of a. So you're saying that when you start, you have to be in a state where y bottom is all of y and is equal to a times x plus y hat. But that means that the loop invariant is in a state where you've already computed everything that you want to compute in the loop. Before you even get started, you must be in a state where you've computed what needs to be computed. Obviously not a favorable thing. So, for this reason, you should never have both of these as part of your loop invariant for this operation. For a similar reason, you should never be in a state where neither of them are there. For example, what if you made it that? The problem then is that you can't find the loop guard if you think about it hard enough. Again, because we have to go from top left to bottom right, because we want to maintain these blocks of the matrix as square matrices, and therefore we can't just magically go and try to grow this matrix into the entire matrix so that we've computed everything. Okay, it's the symmetry that gets in the way. So what we just argued is that a loop invariant for this operation inherently has to have the term in it that references a top left, and not the term in it that references a bottom right, or vice versa. It has to have the term in it that references a bottom right, but not the term that references a top left. Because only those loop invariants will actually give you a valid loop guard and a valid initialization step. So if you take that into account, then you can get rid of half of the candidate loop invariants that we had in the previous table, and you're left with these 8 loop invariants for which you can then go and derive algorithms. And that's what we'll talk about next. What we'll do in the next video is pick loop invariant 1, which you then fill into the worksheet, and then with that we will derive the other parts of the algorithm.